So there are literature available in the different sources, online, offline sources. So we can see that. Here we can basically, whenever we can say mathematical biology, it's nothing but an ecology, right? So it is an interaction between the species. With respect to what? There may be a competition between the species, right? So model will have some assumptions. Under certain assumptions, we will say that this model will work. It's not a thumb rule, it will work for everyone, right? Like everyone we used to have, one can get the temperature, like kind of this. So once everyone temperature, we can have that paracetamol, right? Kind of things. So it will not be like in a mathematics, right? So we have the situations, which situations satisfy these particular equations, right? So therefore we'll have some assumption. Under that assumptions, we will propose some models and we can check with the realities either this model works properly or not. So basically there are two kind of models. One is called as a deterministic model, another is a stochastic model. Basically any researcher develops the model, so basically he or she develops the two kind of model. They will go either deterministic model or they will go to the stochastic model. So all these models comes under the dynamics, because dynamism is involved in that. Each and every sector with respect to the time interval, the phenomena are changing, right? Suppose the population in one forest, population of the deer, population of the rabbit, population of the tigers, it is a changing. So dynamism is there. The organism which are the going on the foods, if you could see in the morning, they are different. Now in a summer season, if you can see, the growing of these bacteria is very high. So therefore it's a dynamism is there. So at every time of interval, the phenomena is changing. The population of that particular species is changing. Study comes under the dynamical model or a dynamical system, we can say. So what mean by the deterministic models? Through the use of such a model, one can study from the solution whose outcome is certain. We know the outcome is coming from this model is a fixed one. It is a fixed one. For example, in a bacteria, in a bioreactor, bacteria, if glucose is added at a fixed rate D, the bacteria's growth can be added by using the model. Similarly, another it is giving, if you can, if some food is lying in our home and we keep that plate as it is at the basin, right? Initially, at the initial stage, the bacteria will grow very fast, but the food is limited in that plate. After a certain time, it is again declines, right? So we can predict that. We can predict that by using this model. So therefore, we call this as a deterministic models. Second is a stochastic model where you can forecast, where by using some probability estimators, you can estimate it, you can forecast it. It may not be exact, right? It will not be a fixed one. These are the possibilities and probabilities, depend on your different estimators, right? Suppose some examples are already given. So in this, so all these phenomena will come. Like if somewhere the natural disaster happens, then death of that species will be very high. Correct? So which is mentioned over the same in the particular examples. So that, how we formulate that, how we can model that, so that we can model by the probabilistic approach. Therefore that's we call as stochastic models. So these are the, is it visible and is it readable? Huh? Now it's fine, right? So this is the basic difference between the deterministic model and stochastic models. So as per the definition of the deterministic model, it's predict the exact outcomes from these models, whereas in a stochastic model, because stochastic models are based on the probabilities, so randomness is there, right? Then there will be the randomness will be there. So basically the particular equation which comes from the deterministic models are nothing but the differential equations, whereas in a probabilistic model they are not in a differential equations. So both are, this is deterministic models are applicable for the and stable environment, means more irregularities will not be there in case of the deterministic, where in stochastics small populations will be there and fluctuations will be very high. Similarly, if you could see their graphs also in a deterministics, the solution graphs which are going to come through the model will be a smooth solutions, means function is a smooth function, so you can get a smooth graphs and they are continuous. In case of the stochastics, you will get a irregular fluctuatings, and about the predictability, it is exact, it having a multiple things because it is probability based approach. So this is a single species model. So here we have made some, it is not happening usually, but let's, the start of this mathematical biology is start from the single species model, right? So what are the considerations we have done here? If you can read, one can realize the single species experiment can over a period of time is proportional to the population of species at that time, right? So we have made some assumptions. First, where we are carrying out this particular experiment, right? Where the rate of change of the population over a period of time is proportional to the population at that time, right? So assumptions we have made. So therefore, so I can get first order equation into n, and if I put b minus d is equals to lambda n, so this is the simple first order differential equations, right? Now we know how to solve. Just if you can get the integration over a time t, and so you can get the solution n is equals to c into e raised to lambda t, where lambda we called as an biotic potential, which is the difference between b minus d. What is b? B is a birth rate, d is a death rate, and we have assumed that birth rate is always greater than death rate. These are the assumptions we have made. So c is any arbitrary constant. To remove that arbitrary constant, so let consider some initial population, right? Consider some initial population at a time t0. There was some population, we will fix. So therefore n0 is the some initial population. If you replace that constant c, you can get exact solution n of t is equals to n0 e raised to lambda t, and this is we called as an Malthus equation or Malthus dynamic equations, which is the first equation provided, or which is the first equation came forward by provided by in a dynamics model, right? So but if you could observe that solution properly, n is equals to n naught e raised to lambda t, where n naught is some constant which is the initial population. Right? It may be any 100, 10, 20 constants. Right? But if you could see e raised to lambda t, right? Time is passing, time is going on. So if I take time t tends to infinity, so my population becomes an infinity, which is not possible at all, which is not possible in a realistic sense. Therefore, this model has ambiguity. Therefore, this model is an unrealistic model. Right? As my time is passing on, then this becomes as an infinity. Population becomes infinite. So, which is not possible at all in any circumstances, at any physical situation or any biological situation. Therefore, this model having some problems. With respect to that, here we are trying here to put some values of the lambda. So already we know that n of t is equals to n naught into e raised to lambda t is our solution, right? If I fix lambda means that difference. So difference lambda is equals to supposed to be a minus 2. Means what? If your birth rate is less and death rate is more, correct? It's coming negative means that is only. Whatever the value of either 2 or 100, minus is there, right? Means where birth is less, death is more. In that case also, if your time tending to, as time varies, the population is declining. So in the second case also, if you take very small quantity of this rate of change, again as time passes, the population is going to vanish. So how much unrealistic approach is lying over here, we can see. Similarly, if you take a positive, means birth is more than death, there also you can get the sudden changes of this one. If you could see because it is exponential order, so the growth of the function is very high, the rate of the convergence of the exponential function is very high. As time passes, you can say that sudden change is there. Similarly, if it changes the again birth rate more, the line becomes more sharp. So convergence is again more faster than the earlier one, right? So therefore, which is unrealistic one, right? The sudden growth of the things. So therefore, this is the geometrically we can say how the Malthus model fails to explain the correct or correct physical phenomena or biological phenomena, we can say. Then we can replace this lambda, which is an absolute positive constant, with some functions, right? If we try to lambda, we can take as a function of n, means it is again a function of the population at a time t. If we could do that, and if we can replace this f of n is equals to a minus b, right? Earlier was a minus b, right? So now if you could see, this is a is your birth rate, b is a death rate. So now this is interacting here, where the death as well as population at the time, it's the interacting at the over here, that terms. So simple again manipulation, mathematical manipulations, and simplified these terms, then we can get some simplified version of this one, right? n is equals to this one. Now let's take again same situation is going to happen, because as we are mathematicians, so we are having a general habit. What will happen if my t tends to infinity? Right? Every time we see that at the infinity, how the things behaves. Right? So similarly, if I take here as my t tends to infinity, so this term is going to be a 0. Right? Because this is already minus is there, minus at, so this term is going to be a 0. So now what is the remaining? A n0 upon b n0. Again this n0 is some constant, so it is going to be cancelled. So this will become an a upon b. So that is called as t tends to infinity, the population size reaches to its saturation level. as t tends to infinity, the population will be reach at a saturation level. After that, there will not be any growth. So after that, your graph will become a constant, right? So that value will be A upon B. I don't know either. So then if you can rearrange the same earlier equations, put all these things, and if you could simplify this, so this will becomes like this. Right, the same model, if you can rearrange, this is just mathematical simplifications we have done, not much anything. And here if you could see this, as we said, this is A upon B is a saturation point of the population, and we are calling that as a carrying capacity, which you called as a capacity. So carrying capacity of every individual is also have some limits, right? That you can take carrying capacity in that sense as well, right? Beyond that you cannot carry. Under some observations, suppose if I am having some bacteria growth I want to do in one closed room with all the environmental conditions, so it will not go beyond that. Having that, it will not go beyond that. So that is the meaning that the carrying capacity of that particular model, right? So sometimes it is called environmental or carrying coefficient of the populations, right? So we'll check how this carrying capacity or how this model is works well as compared to the earlier things, and how it is the best one. So we'll see some of the things. Again here there are some of the situations is mentioned with respect to the relation between N0 and AB. So I will not go in detail with this exercise. Representing see so many different kind of situations. If you can see the earlier model where the carrying capacity was there, as we mentioned that it will not go beyond the carrying capacity, right? Any natural phenomena. So if you can see in the first case, my N0 is 1, means my initial population is I am considering 1 over here, and K I have fixed carrying capacity of that model is supposed to be 100, right? And B is equals to A upon K. B is equals to A upon K, right? So if you can see here, as time varies, so I consider the interval between time interval as a 0 to 10, and here in y-axis is the population. If you can see, whatever the A, different A's are there, so all are converging to this. K is equal to 100. No graph is crossing this 100, means it is not going beyond that. Those our A and B are varying different, right? Because here also changing to K, here A also we are changing, so it is not beyond the capacity. Similarly, if suppose we can check, if I am considering the initial population, initial populations, right? Initial population is 40, 50. If it is 100, if my initial population is 100, then there is no growth. There is a constant, right? That is a constant, and you can see if I am taking my initial approximation beyond the carrying capacity K is equals to 100, so also it is declining and it is to 100 only. As time increases, so the population is decline, and which is the stable at a K is equals to 100. It will not go beyond the carrying capacity, That's the interpretation I want to do with respect to this different initial approximations. So similarly here again we have changed the only the range of the A. Earlier it was the same figure. A is equals to 2 to 10. Let me just check. Now here A is 1 to 10, but here A is equals to 1 to 2. Right? With respect to all the initial populations, only we have 1 to 2. Also the model works properly. Model works properly, therefore this is one of the best model we can say for the population dynamic model for single species, or this is what we calling as a logistic growth model. This we are calling as a logistic growth model. So in this whole, whenever we are studying the model, so we should know about its stability, or that is called as an equilibrium point. Right? That is nothing but the equilibrium points. So how we can find that? So we can say that we consider first derivative is equals to 0, and we'll try to equate and try to find out the points. So here if you equate with the 0, n is equals to 0 and n is equals to k, these will be the trivial points, and if you put the n is equals to 0, the population is extinct, and if you put n is equals to k, the population stabilizes its carrying capacity, as you can see in earlier example also. Therefore in this model, n is equals to k is the stable equilibrium, meaning that the population is perturbed slightly, it will returns to the k. If you are having some perturbation also, perturbation is a small change, or you can consider a small error in that also, in that case also this model will work and you will get the stable solution. So this is another model which is called as the interactions of the two different species. Right? Whatever we were discussing, that was the single species only. Now here there are two species. In one species, that is called as a host. H is called as a host and P is called as a parasite. Or sometimes we called as host is nothing but the prey and predator. Right? So in one forest, deer is there and tiger is also there. A rabbit is there, who will eat the rabbit, that fellow is also there. Right? Likewise, so we are considering here two species which are interacting each other, and then we are trying to get the model for that. So if you see the first equation, dH by dt is equals to A1 minus B1 P into H. So A1 is anyhow is a birth rate. Right? So now dH A1 into H is a positive quantity. Right? What is H? H is the host population. H is the host population. This quantity is a positive quantity. But there is one more term which is a negative with this one. So there is an interaction between host and parasite. If deer eats the tiger, what is going to happen? Population of deer is going to decline. Correct? So therefore that's why we are putting it here minus. Interactions is happening between host and parasites. So interaction between these species, so therefore the population is going to be down. So that's why we are setting here minus. Similarly, parasites. So if you could see, I think we have made some assumption also. If I want to read, the parasite species on the other hand can not grow on its own, right? Let me read, that's why it is important. So we consider the types of the interaction between the two species, where one species is being fed by the other. One of these is called as a host, which is called as a prey, and has the intrinsic ability to grow on its own, but its growth rate is inhibited because of its interaction with the parasites, that is called as a predator species, which is used first as the food. So the parasite species on the other hand cannot grow on its own. These are the assumptions we have made. Obviously increase because of its interaction with the host population. So let H and P are this. So here if you can see, this is a parasite. Parasites will grow by its own. Therefore parasites into this P is a minus. But here if you could see parasites into H, it is a positive quantity. Whenever parasite is interact with prey, their population is going to be increased. They will eat, they will sustain, and they will increase. Right? So therefore this is called as a population dynamics between the two species. One is a host, another is a parasite. So I feel it is clear about this. And all these parameters which we are considering A1, B1, A2, B2 are called as logistic parameters. So now again let's try to see how to find the equilibrium points, or you can may say critical points. So the model which we have discussed just now is called as a model. These are the two independent scientists who were discovered this during the 1920s, but while developing this model they have made some assumptions. What are these assumptions? This model is based on simply assumptions such as that predators only eat one type of prey and that prey have unlimited resource other than predators. So parasite is always dependent on prey, and prey will have all the other resources except parasite. Right? This model is used by theoretical ecologists to study how different species interact in a fixed inhabitants. So now again here we will do some manipulations to get the critical points and where this model gets stable, what are the stability conditions and all this stuff. So the meaning is that it is equals to 0. When we can put equals to 0, then you can get critical points, right? So therefore by using the simple derivations you can get critical points. So if you could see in both the equations we are trying to put the derivative is equals to 0 and equate to 0 and get the critical points. Sorry, how I am not getting this. Sir, therefore if you could see 0, 0 is a trivial. We are able to find these are the two critical points. One is A2 upon B2 and A1 upon Bn. In these 2 points you can get a stable solution for this population dynamic model. So I will skip some of this part. So if in this particular case if you put some values for A2, B2, so in that cases you can get these critical points. And if you see it's in a graphical, there are to check these stabilities of these particularly population dynamic models, you will have the different kind of checkpoints. One by graphical way is called as a phase plane diagram. You might be aware that whenever we are studying the differential equations, so there also will have the directional fields, right? We will have the directional fields. Based on the slope, we plot the directional fields, and based on the slope, you will get the directions, and based on the directions, so we can reach to the solution of the differential equation, stable solution of the differential equation. Or you will get the, for each different points, you will get the different trajectories, different directional fields, and if you can connect these directional fields, is nothing but the trajectories. You will get the different kind of solution. As how the constant c Cummings, if you can take the integration of the first order differential equation, you will get e raised to lambda t and plus some c. For every changing c, you will have the different solutions. Correct? So that same solution we can get by through the directional fields. Correct? So similarly, that same called as a phase planes. Right? Here if you can see now, you can read this writings whatever I am saying. So I think this figure is, we are trying to plot the phase plane of this particular model. If you can see, these arrows are going to this. The arrows are going to the right hand side. If the arrow points right, the prey population is increases. This is for the x-axis, it is a prey population. For the y-axis, it is a predictor populations. So on the directions of the arrow itself, we can see that either population is decreasing or increasing over a period of time. Right? Over a period of time. If the arrow points are the left, then prey population decreases. Likewise, from this and this point, which is the red one, is called as an equilibrium points, and over equilibrium points, all these directional fields are happening. Right? So let me give few more examples with respect to the same discussion. So now this is a particular example. We'll have a different kind of examples, and then we can study how it's impacting. Does the model is working correctly or not? Suppose this is in general differential equations with I am putting A, B, C and D. Right. So X and Y interaction is happening. Here also interaction is happening. The same model, which is equation number 3 or 4, as a model, which is the same. Suppose in the first case, if we are considering A, B, C is like this, B in case like this, and C like this. Now, so if you can see here, this, let me possibly, if I want, okay, is it fine? So now this is prey population and this is a predictor population. Now if you can closely observe that, suppose this is a blue line. This is for some values of AB between this one, 0.1 and 0.2. So this is a prey population. Between this interval, preys are increasing. If prey is increasing, what about the predictor? What's supposed to happen? It has to be decreased. खाणारे वाढले तर ज्यांना खाणारे भक्षक आहेत ते कमी झाले पाहिजे ना. एका जंगलामध्ये समजा 100 ससे आहेत आणि आपण समजा 200 वाघ सोडले किंवा 200 कुत्रे सोडले त्याच्यामध्ये खायला, तर त्यांचं पॉप्युलेशन कमी व्हायला पाहिजे. करेक्ट. इफ prey population increases here, then its population is decreasing. You can see here the 0 because it is higher. So similarly, you can see in somewhere, if prey population is decreasing between this, then predictor population has to increase between this range. Right? So between say likewise this, you could see this plot is going high. So there is one more phenomena is also there. It is not like that only prey will increase. There is intercompetition is also there. If parasites are more and prey are less, suppose in this closed room there are only 2 rabbits or 2 deers are there and 3 tigers are there, there will be the competition. There will be the intercompetition will be also there. So who will get my food first? So that competition also make them to decrease their populations. They will attack on each other and one of this will be die. So therefore that interaction also there, if you can see in this case, so it will increase again, it will be decrease. This is the phase plot you can see. As a prey population increases, so it decreases, here then again it will be increased like that. So this cycle will be changes according to their different dynamics. So similarly you can take any different examples. So I have made 2 case studies over here. So in each cases you can check the same kind of phenomena is happening, right? The same kind of the means Locta-Volterra model is best model to study the prey predator between the 2 species which interacts with each other in that some assumptions which we have made. So only now these are the only different values, only changes, nothing else. The same kind of the models are there. Similarly, if you consider some perturbations, then how to get the equilibrium point? There is another method to get the equilibrium point, that is called as a perturbation method. So that is again some mathematical manipulation is there. So I will not go in detail with that. So if you could solve all these things, so you can get the different equations, and similarly you can get this second order differential equations. Once you will get this second differential equations, we know that clearly we can see the auxiliary equation is d square plus this, you can what it may be, or m square this. So you are going to get a complex root, so therefore their solution will be in the form of this trigonometric functions. So I will skip this part and let me only describe one more phenomena in that. So now we have considered there 2 species, right? There are 2 species. There is thing is also their migration, right? Over a period of time, if I am not getting a sufficient food, either prey or a predator, whomever, they will migrate. Or sometime they will immigrate also. Sometime they will come or sometime they will go in search of foods. So that we are considering here plus epsilon and epsilon 2, and again we can work the similar ways what we have done in earlier case, and that another case we can discuss the same. So again I will not go with the particular model. This is a competitiveness model which I have just discussed. That is same, we cannot say like an unlimited growth over here. There is self crowding effect also. There will be some detrimental effects will be also existed. So likewise you can develop the different models. So I will skip this part, and just as I thought to have to just show some of the models which are the again differential equation models. So this is very well known model that is called as an SIR model. So where susceptibility of the individuals who can infected individuals and disease. So this is the very basic model based on the different diseases, their spreading rates and all other rates, all parameters. This model changes different ways, and then which can form different equations, where again these are the different parameters, beta, gamma, and all these things will be there, and based on that, what is the rate of infections of this disease. Likewise, you will get the all. This is I have, rather than say copied, I have collected from the literature and I am presenting in front of you. Similarly, there is now, as a lot of people are doing in a fractional calculus, so these are the few fractional order pre-predictor models. This is the fractional order pre-predictor models. Now you could see in earlier models, we were discussing about only their interactions between the two species. But this particular model is going beyond that. What are the different environmental effects on these species? Right? Like, suppose climate changing is happening. Right? Lot of pollution is there. So in that circumstances, how this model works? Right? So the temperatures are, so many ecological conditions are changing. Right? So how they will, and in that situation, how the predictor model will work, and to represent that, again they were using that differential operator by using a Caputo fractional derivatives of say order q. Right? So already all these constants are, I think I will not take a much time on that. So if you could see what is the effect of the temperature on this particular species, extreme weathers. Earlier, if you could ask in our forefathers, or our parents, or those who are elder, they will say that at a 7th June they used to get a first monsoon, but today you can't predict. Right? So there are a lot of changes are happening over a period of time. So we have to add some of the things. Right? So therefore that things is trying to adopt in this particular models. This is another model called as, this is with respect to the global warming, and again here also they have used as a non-regular fractional order model, and specifically Capito-Fabruzo fractional derivative they have used for this particular model, and what are the different parameters are given. I will share this PPT, sir will share in your group. So if those who are interested, so they can go through that. So all the references, literature, all things we have mentioned in this presentation. So this is just, this particular session was made to put some of the different models which provide the relations between biology or ecology and mathematics. That was the basic objective, to introduce the different kind of models are also existed, where we can go and attempt that and get a different kind of research in these directions. That was the basic objective of this particular presentation. So these are the main references. So with respect to the mathematical biology, these are the 3 books which I mentioned. And with respect to fractional, these are the basic and initial. There is one more book is not printed over here, which is Podlubny's book, which I offer. So that is very famous one. Everyone is known about that. So these are the few references, and these are the some of the top journals in the field of the fractional calculus. If anyone want to do any kind of the fractional research, so just go through these 9 journals, you will get the best articles. This is the topmost journal which is highly cited and having high impact factors, which is the top journal. If you are having real innovative ideas, and if you submit any your manuscript in this journal, it may takes almost 2 years to get it published, right? So that much of huge queue for the publications. So at the last, I thanks to the principal of the Science College as well as my all colleagues, Gaikwad sir and HOD sir, Chopade sir. So I am really thankful to them for giving me this opportunity, and I cannot say to interact with you because you cannot have any interaction with me. Actually, it should have some interaction between two theses as model suggests, otherwise my model will get failed. If you are having any questions, please, it is open for the discussion. Yes. Okay. नाही बेसिकली झालंय असं की जे काय आज रोजी जवळपास 5 ऑपरेटर्स फ्रॅक्शनलचे आज लिटरेचरमध्ये आहेत, करेक्ट. त्याच्या मिनिंग आपल्याला पहिला समजून घेतला पाहिजे. आता आपण जस्ट सगळेच जण इन्क्लुडिंग मी, आपल्याकडे फक्त एकच ट्रेंड आहे, जिथं डेरिव्हेटिव्ह दिसते त्याला काढायचा, कपुटो लावायचा, रिमन लिव्हिल लावायचा, हार्डमार्क लावायचा, करेक्ट. पण रिअली डज इट मेक सेन्स ऑर नॉट, दॅट इज अ क्वेश्चन. व्हॉट इज द बेसिक फिजिकल इंटरप्रिटेशन or physical phenomena which covers by the fractional, that we have to address. For example, let me tell you how this fractional derivative should be utilized, in which situation we supposed to apply these phenomena. For example, if there are two different solutions are there, right? If there are two different solutions are there, I am mixing these two solutions, that we call as a diffusion. If I am mixing milk with the water, I am mixing water with the ink, there has some diffusion process happens. Diffusion throughout this liquid, correct? So does it apply that physical phenomena which is called as a diffusion law? Does it satisfying that proportionality of that rate of change is happening or not? If it is not happening, then there is something different. That's we call it as a super diffusion or a sub diffusion. So in that case, in such situations, your fractional derivatives arises. Likewise, we have to see what that phenomena is there, what it's going to be interpreted, what is related with some physical phenomena. Then and then we can assure that what I am doing it is a correct. But as I mentioned, the trend is like that, just to replace the derivative, usual derivative, put there couple derivatives, then either use the Laplace, do the numerical, because anyhow it's integration representation is there. We know integration can be written as a summation and make it a discretization, so you will get a numerical solutions. We know the Laplace, apply the Laplace, get Laplace situation and again get the solutions, or use some approximation kind of things. So those things are there, but really if you want to see, then Physica is under elsewhere journal is there, where such a kind of so many physical phenomena where exactly where the fractional will be arise, right? So they are having bit ambiguities lying in the subject, but till it is going and it is a publishing, that's another way, right? Thank you for your nice question. Please seated.
Sir, in autonomous model, we have parameters and they are constant in nature, autonomous. So how to choose, how to give value to that parameters? Is there any criteria?
Okay. Because as really I want to say, then I haven't worked in this autonomous model or autonomous system, basically, right? हाँ, correct.
And one more question is there.
हाँ,
Convert our original equation, our original system of equation into non-dimensional form. So what that non-dimensional form does on our original model? Means what is the difference between the solution which we get directly from the non-dimensional form of the model?
okay. I read it about, but right now I can't recall it. But I will note it and I can message you. I understood your question correctly. That's not an issue.
Mainly when our paper goes for the review, so in my papers there I face that
Okay. That's why I'm saying, see, research in the mathematics is very precise and very particular. If I say differential equation, some of the differential equations results it's not able to me explain or not able to understand at the same time. Because the focus is very precise and very particular. Those who are working in the core areas, they only can give you correct answer. Right? The person like us, whomever we are talking, we talk the general. We will not go in at the point of the research, right? So it depends on if both the areas are same, then we can have the discussion, correct? No issue, please.
for the research purpose. We convert our what integer order into fractional order and we calculate those and all this. But actually for this area, this it may be is what possible for physics or other subjects, but for biological modeling, this needed to convert means what is the geometrical interpretation behind that?
Geometrical interpretation.
We do its calculation and we get answers and
Yes,
research papers and publish everything we
get correct.
But what is the like आपण सांगू शकतो का त्याचं महत्त्व काही?
सांगू शकतो ना, का नाही सांगू शकत? काही त्यासाठीच मी त्यांना ते रेफरन्स दिला, फिजिका ए मध्ये जा तुम्हाला.
स्पेशली बायोलॉजिकल साठी बोलत आहे, बायोलॉजिकल मॉडेलिंग साठी बोलत आहे.
आता आपण 2-4 जे एक्झाम्पल दिले जॉमेट्रिकली सांगितले ना, एक पॉप्युलेशन इन्क्रीज होत आहे, दुसरं डिक्रीज होत आहे, ह्याच्यापेक्षा वेगळं काय तुम्हाला पाहिजे मला? हां, यस प्लीज सर. Yeah. ते करायचं म्हणलं ते वेगळ्या पद्धतीने रिसर्च करावं लागेल. हां, ते सांगतो. यू हॅव टू इन्व्हेस्ट द टाइम. त्यांचा नाही. या, थँक्यू थँक्यू.
ॲक्च्युली जे सगळे बायोलॉजिकल मॉडेल्स आहेत, प्रिडेटर किंवा सर मॉडेल किंवा खूप असे मॉडेल्स आहेत ज्याचे ॲप्लिकेशन्स आपल्याला डायरेक्टली दिसत नाहीत, परंतु त्याचे ॲप्लिकेशन्स विचार नाही नॅचरल फेनॉमेना आहे तो डेव्हलप करतो. हां, आता थोडं केले की आहेत किंवा जे सगळे आहेत ते सगळे किल आणि त्यांनी किल केले आणि ते किल केल्यामुळे काय झालं की जे छोटे आहे आदिवास आहे तिथे आले आणि त्याच्यामुळं किल द स्पॅरो so ecosystem is disturbed. But we will give in the geometry, but that is not all geometries are they are to be predicted, that they are not actually to be done or that to be exactly true, like our differential exact solution, but we cannot say that it is exactly the solution of that system, but we are trying to face it or we are trying to improve it. It may be used somewhere or it may be explained in geometry and anywhere. Okay,
Basically, as I mentioned, any model under other automatically the model behaves. That's that.
Okay, thank you so much for giving this informative and interesting talk. Now, I am thankful for organizer to giving such a wonderful session. This is very, very fruitful for, most importantly, for the students. So once again, thanks to all of you. And with this, I declare the session is over.
क्लोज करणं वर शट डाउन कर
ऑनलाईन